In this video, we will talk about the waiting line model calculations. For every queuing models, we often know some basic information about it. The first one is the configurations, such as how many servers are in the store, how many waiting lines, and such. The second one is the arrival information, including the arrival distributions and the arrival rate, and we often call it lambda. Finally, we need to know the service distributions and the average service rate, and we often call it mu. Once we know the basic setting of the queue, we can calculate its performance. The first thing we usually calculate is the utilization rate, denoted by rho. The utilization rate is also represent the probability that the server is busy. And secondly, we can calculate the average number of people waiting in line, denoted by LQ, and the number of people in the system, denoted by LS. Finally, we can calculate the average time a customer needs to wait in line, denoted by WQ, and the total time in the system, denoted by WS. For some specific queuing setting, we can even calculate the probability of having n customers in the system. So how do we do the calculations? For the utilization rate, it is pretty straightforward. The formulation is the arrival rate divided by the service rate. Also, the waiting time in the system is equal to the waiting time in line plus the service time. And in addition, we can use Little's law to figure out the relationship between the number of people and the waiting time. That is, LQ is equal to lambda times WQ, or LS equal to lambda times WS. In English, the number of customers in line equals to arrival rate times the waiting time in line, or the number of customers in the system equal the arrival rate times the total time in the system. Finally, we can use Kingman's formula to calculate the waiting time in line. Note that the Kingman's formula is also called UVT approximations because the first term is about utilizations, and the second term is about availabilities, and the very last term is about the service time. UVT approximations can be applied to different settings. For instance, we are listing the two UVT approximations for Model 1 and Model 2 that we are going to discuss next. The Model 1 in the textbook is based on the following assumptions. We assume we have Poisson arrival and exponential service time with only one server. This setup is also referred to M1Q, where the first M is used to describe the arrival distributions, in this case is Poisson arrival, and the second M is used to describe the service distribution, which we have exponential distributions. The number in the end means that we only have one server. Once we know the setup, we can figure out all the calculations shown on the slide. Now, if you look at the formulation carefully, you will notice that we literally only use two formulas. The first one is to figure out the waiting time in line using the UVT approximations. Then we figure out the waiting time in the system by adding the waiting time in line plus the service time. Finally, we calculate the number of people in line or in the system using Little's law. Now, let's see an example on the next slide. Now, let's take a look at the first queuing example. Western Bank has a drive-through window for customer service. Management estimates that the customer will arrive at the rate of 15 per hour. The teller who will staff the window can serve customer at a rate of 1 every 3 minutes, assuming we have Poisson arrival and the exponential service time. We want to find the utilization rate, the waiting time, and the number of cars in line, something like that. So how can we solve this problem? So first, we notice that the arrival rate will be 15 and it will be the Poisson arrival, and the service rate will follow the exponential service time. So basically, we know this is M and 1Q. Remember, the first M stands for the Poisson arrival. Second M will be the exponential service time. The third letter, number 1, means that we only have one server. And when we try to solve this type of problem, the first thing we want to do is to realize what will be the utilization rate. And we know the arrival rate can be denoted by lambda. In this case, lambda will be 15 per hours. But if you read the problem carefully, you will notice that everything will be described in minutes. So the first thing we want to do is to convert this to minute. So I have a quarter arrival per minute. Okay, and we also see that the service time will be 1 every 3 minutes. So every 3 minutes, I will be able to serve 1 customer. So we don't have service rate here, we have service time. Service time will be 1 over mu. And this one is equal to 3. Okay? And in other words, our service rate, mu, will be 1/3 per minute. So I will be able to serve 1/3 of customer every minute. So once you know lambda and mu, we can figure out the utilization rate. And we call utilization rate rho. Rho will be equal to lambda divided by mu. In this case, we have 1/4 times 3, which means the utilization rate will be 0.75. So on average, the server will be busy at 75% of the time. Okay, so when you go to these locations and the probability of 7.75, you will find that the server will be busy. The remaining 25%, you will realize that the server is not busy, so you don't have to wait. And the first thing we want to calculate here is the average waiting time in line. And remember the formulations for that. The waiting time in line means we want to calculate WQ. Q means the queue, so WQ will be the waiting time in line. And since we have MN1Q, the formulations is actually equal to rho divided by 1 minus rho times 1 over mu. You can find the formulation on the previous slide. Okay, so we just plug in all the numbers. 0.75 divided by 0.25 times 1 over mu, which is 3, and the answer is equal to 9. And the unit will be minutes. So your average waiting time in line will be 9 minutes. Once we know the number, the waiting time in queue, we can also calculate the number of cars in line. So remember, if we want to calculate that, we want to find out LQ. LQ, the number of person or the number of car in line. And we can use the Litto's law. So LQ will be equal to lambda times WQ. In this case, it will be a quarter times 9. So I have 2.25. The unit is cars. Okay. If you knew WQ, you can also calculate the average waiting time in the system, and we call this WS. And based on the formulation on the previous slide, we know WS will be equal to WQ plus 1 over mu. This makes sense because your average waiting time in the system will be your average waiting time in the line plus your average time you get served by the server. So in this case, I have 9 plus 3, which is 12. The unit is minutes. Once you know WS, you can calculate LS, the average number of cars in the system. And again, you apply the Litto's law. I know LS is equal to lambda times WS. So in this case, it will be a quarter times 12. That will be 3. So on average, there will be 3 cars at these locations. Finally, for the MN1Q, we can also calculate the probability of having a certain number of cars in the system. So if we want to find the probability of having less than 3 cars in the system, basically we want to find out, let me write down the formulation first. So we denote Pn equal to 1 minus rho times rho of power of n, and Pn will be the probability that you have n cars in the system. So in this case, we actually want to calculate P0 plus P1 plus P2, because the probability of having less than 3 cars in the system means that the probability of having 0 car plus the probability of having 1 car plus probability of having 2 cars. Okay, then you just plug in all the formulations. This is equal to 1 subtracted by rho times rho of power of 0 plus 1 subtracted by rho times rho power of 1 plus 1 subtracted by rho times rho of power of 2. Okay, so everything here will be equal to 1 subtracted by rho times rho 0 plus rho power of 1 plus rho power of 2. Then you just plug in the number. This is equal to a quarter times 1 plus 3 over 4 plus 9 over 16. That should be equal to 0.5781, and that will be the final answers. In the Model 2, assumptions are almost identical to Model 1, except for the service distributions. In Model 2, we assume that the service time is a constant. This type of model is also referred to MD1Q, where D stands for deterministics. Since the service time is constant, again, you can use the Little's law and UVT approximation to find out everything shown here. Now, let's take another example. Basically, the second example has the almost identical description from the first one. The only difference is that now we assume we have a Poisson arrival, but a constant service time. So for every customer, the service time will be exactly 3 minutes. So this is what we call the MD1Q. So we have Poisson arrival. D will be deterministic, so we have a constant service time, 1 server. Okay, and the only difference of this problem and the previous one is that for the WQ, the formulation now become rho 1 subtracted by rho times half times of your 1 over mu. All right, so remember, the lambda here will be 15 per hour, or a quarter per minute, and the service time will be 3 minutes. And everything will be identical to the previous one, except for this formulation here. So we know the utilization rate will be lambda divided by mu. That will be 3 divided by 4, which is equal to 0.75. The average waiting time in line, we are going to use a formulation of both. So WQ will be equal to rho 1 subtracted by rho, half of that, and the service time. In this case, it will be 0.75 divided by 0.25, half of that times 3. So everything here will be equal to 4.5 minutes. Okay, and the average number of cars in line, again, we use the Little's law. So LQ equal to lambda times WQ, and that will be a quarter of 4.5, which means I have 1.125. The unit is cars. The average waiting time in the system, WS, is equal to WQ plus 1 over mu. So I have 4.5 plus the service time of 3 minutes. That will be 7.5 minutes. Okay. Finally, the average number of cars in the system, we can apply the Littl's law again. LS equal to lambda times WS. So I have a quarter times 7.5. So everything here will be equal to 1.875. Again, the unit here will be cars. Finally, in Model 3, we call it MMKQ. The reason is that we assume we have Poisson arrival and exponential service time. Also, instead of having one server, we have K servers. To solve the MMKQ, we can still use UVT approximations. However, to make things easier, we can look up for the answer using a table provided in the textbook. Now, let me show you how to do it in the next example. So in this example, the Western Bank has a drive-through window, so the same as the previous two. And we know the customer will arrive at the rate of 15 per hour. So arrival will be 15 per hour. That will be a quarter per minute. And the service time for each of the teller will be every 4 minutes. So 1 over mu will be 4 minutes. But here we have 3 tellers. Okay, so basically we will have 3 servers. And we again have a Poisson arrival and exponential service time. In other words, in this example, we have a typical MM3Q. So exponential arrival, a Poisson arrival, exponential service time, and 3 servers. And in order to solve this type of problem, we can use the table provided in the textbook. So in order to do that, the first thing we want to do is to calculate lambda over mu. In this case, it will be equal to 4 divided by 4, which is equal to 1. Then in the table, you can look at the value where the lambda over mu is equal to 1 and the number of servers is equal to 3. And you will realize that the corresponding value will be equal to 0.0454. So we know the average number of cars in line, LQ, is equal to 0.0454. Okay? Once you know LQ, we can again calculate WQ. And we want to use the Little's law. So where we know LQ is equal to lambda times WQ. So WQ is equal to LQ divided by lambda. So in this case, we have 0.0454 divided by lambda divided by 1 over 4. And I have 0.1816. The units will be minutes. Then you can use the same formulations to calculate the WS. We know WS is equal to WQ plus 1 over mu. So I have 0.1816 plus 4 minutes. I have 4.1816. And we use the Little's law again to calculate the average number of cars in the system. LS equal to lambda times WS. So I have a quarter times 4.1816. I have 1.0454, and the unit will be cars. The next topic we want to discuss is called capacity pooling. Here we want to consider two systems. In the first one, it is very similar to the grocery store, where you have two separate lines and two separate cashiers. We assume the arrival rate to each line is 4 per minute and the service rate is 4.5 per minute. In the second system, we combine the two lines together, so we have one common line and two separate cashiers. Because the two lines are combined, the arrival rate is now 8 per minute instead of 4 per minute. Each cashier can still process 4.5 customers per minute. So the question is, which one will provide a better service? In the first scenario, we can use Model 1 formulations and get the waiting time equal to 1.77 minutes and the number of people in line equal to 7.11. In the second scenario, we use the Model 3 formulations and the table to get the waiting time equal to 0.959 and the number of people in line equal to 7674. Then, when we put the result together, side by side, we found that the second scenario has a much shorter waiting time, although the line size is slightly longer. This is what we call the capacity pooling. In other words, when we are able to combine all lines together, we can actually reduce the customer waiting time significantly. However, the line size will be longer than the case in which we have separate lines. So you may ask, if capacity pooling is much better than the separate lines, why we are not seeing that everywhere, especially in grocery store where we have separate lines everywhere? Well, the reason is pretty simple. When we use the common lines, the line will be longer and it takes up all the space. For the grocery store, it actually makes more sense for them to use the space to store the items for you to purchase. Besides, the store may not have the incentive to shorten the waiting time. Remember, the longer you stay in the store, the more things that you are going to buy. That's the reason.